Hello, my name is Gab, and for this presentation, I will be discussing granularity of locks and degrees of consistency as mentioned in Jim Gray's paper of the same title. And uh, some simple examples were also taken from the supplementary resources, which are shown on the screen, but the bulk of the paper still comes from the main source. Now, the concept of locks and degrees of consistency is central to concurrency control due to the basic limitations that resources cannot execute read and write operations at the same time. Concurrent transactions need to be managed using locks, and if not managed properly, we may not achieve the level of consistency we require. So for this presentation, I will be using this outline for both of the topics, one for the granularity of locks and the other for the degree of consistency. I will mention about the background and motivation of each topics, the contribution and key points of the paper, and the examples to explain these things properly or in simpler manner. One challenge in managing locks is choosing the level or granularity of lockable units in order to make efficient use of our database resources. It is basically finding the right balance of concurrency or number of parallel transactions executed and the overhead or the number of locks made. When we design locking with fine granularity, we can achieve high concurrency since we execute resources down at the atomic level. However, the volume of transactions that is occurring increases the overhead. The opposite is observed when we have coarse granularity. Although we have a few number of locks, this level of granularity is not fair for transactions who only needs to lock a portion of the chosen granularity. So the question is, how can we find the fair balance between the two? That we ensure high concurrency than a usual coarse granularity, but at the same time, we only write locks when necessary and not because we are limited by the level of granularity we selected. The idea of the paper is to make sure that we have lockable units of different granularities coexist in the system. This means we should not make the same decision for all types of transactions. We should allow data items to be of various sizes, whether a transaction wants to lock only a specific record or the entire database. The system should allow both. And this can possibly happen if we use hierarchical locks. Now, Gray's idea would work if the resources to be locked is organized in a hierarchy. For example, a database has area nodes. Each area has files, and each file has their own sets of records. Because of the hierarchical structure, this ensures that each node except for the root has only one parent. So the idea of hierarchical locks is that when a node is explicitly locked by a transaction, it also locks its children implicitly. So here, if area 2 is locked, records C1 to Cn are also locked as a result of locking area 2. The same manner if a transaction locks file B, then locks are cascaded to records under file B, but area 1 is not affected by the said lock. Now, this policy can actually open to some challenges, but before that, let's put some naming on our locks based on the two-phase locking protocol. In this example, let's say that area 2 was locked with share mode and its children, while file B was locked with exclusive mode, and so the records under it. Since locks on nodes automatically locks its children, then we need to ensure that when we plan to lock a node, its ancestors are not locked or is compatible with either the S or X lock. In this example, if another transaction wants to lock record C1 with another share mode, it should allow it so that it's compatible with a currently or concurrently running transaction. So in this case, searching for lockable units would require traversing the nodes from root to the target node before we can see if its ancestors are compatible with the request lock. Second, let's say we found that area 1 is not yet locked and the transaction needs the area 1 to be X locked. Allowing that transaction would lock area 1 on exclusive mode so its available descendants. But as of the moment, file B is still locked with the previous transaction, and two X locks are not compatible to run concurrently. So since area 1 is available, it will attempt to proceed with the request only to find out that one of its children is not compatible with the lock requested. So the transaction will fail and will not commit. The idea is before a node gets a shared or exclusive lock, the transaction must have an idea already of the status of its ancestors. Meaning, the lock manager would have an idea already based on the tagging of the root and as it traverses the children nodes until it gets to its target node. That is when the paper introduced the intention mode. The intention mode tags the ancestors of the target node with intent locks as it goes to the target node. For example, before we can request area 2 to be locked in S mode, we need to request the DB or the parent of area 2 to be locked with intent to share lock. The intention share mode expresses the transaction's intent to get an S lock at lower level or finer granularity. Then we proceed with the transaction of locking area 2 in S mode. Now intent locks similar to S locks are compatible with its own kind, meaning nodes can share multiple simultaneous intent locks. Therefore, if we want to lock file B on exclusive mode, we need to express our intent again at the root of the tree, the database layer. The transaction requests for a lock on intention exclusive mode or IX mode. Then it requests the same IX lock for area 1 until it reaches file B and locks the entire subtree. The intent locks, like in the example, prevents locks on ancestors of a target node. Because of the second challenge raised earlier, doing so freely will execute an implicit lock on another child node which may be locked from another transaction. Now let's simulate the third transaction of requesting area 1 node to be locked on exclusive mode. Starting from the root, the transaction has an idea already that down the path, a node is currently locked. This means that lock manager will park the new transaction without hitting the locked file B until the previously running transaction on file B commits and releases the locks. Once released, then they can proceed with locking area 1 node. The overall setup removes unnecessary commits to the lock table, thus decreasing the overhead. There are also instances when we want to read an entire subtree but update some of its descendants later on. The transaction can either request an exclusive access to the root, which locks the entire subtree, thus losing some concurrency, or request an intent to exclusive access to the root and explicitly locking the lower nodes in intention, share, or exclusive mode. For these scenarios, the SIX or share and intention exclusive mode allows our nodes to be implicitly locked in share mode, and allows requester to explicitly lock the selected nodes in X, SIX, or IX node. SIX combines S and IX modes into one node, which allows the special scenario to exist. This is very relevant for scenarios when we want to update the job titles of employees who are promoted. The query will read through all employees, which is locked on share mode, and then turns all employees with promoted tag to exclusive or intention exclusive mode. Now, the implicit locking of nodes will not work if transactions are allowed to leap into the middle of the tree and begin locking nodes at random. This actually defeats the purpose of getting multi-granular locks happening concurrently. So, there are rules or protocols to follow to make this work. First, we always start at the root of the hierarchy. Notice in the past few slides, for all transactions, we always start at the DB node, and then we make our way down to the target node. Since we want the ancestors of a node to be locked or tagged with intent mode, there are some criteria that need to be satisfied before granting the lock request to the target node. An S or IS lock would require its parents to be on S or IS mode. An X, SIX, or IX lock would require its parents to be on SIX or IX mode. Lastly, when it comes to releasing locks, they are executed from leaf to the root. Lock compatibility and two-phase locking rules are enforced as well. Looking at the compatibility matrix on the left, those highlighted are the original two-phase locking compatibility matrix. A node can have several share requests granted concurrently, highlighted in orange, while exclusive requests are not compatible with another exclusive lock, which is in yellow, or with another mode like share mode, which are in green. These capabilities are extended to support the three newly introduced modes. We can see that X mode is still incompatible with other modes except on null or NL mode when there is no existing access request to a node. A share mode is compatible with itself and in IS mode. So when one transaction locks a node with IS, then explicitly locks its children with S mode, the succeeding transaction which will lock the same node with S mode can happen concurrently, and it will not have any incompatibility issues with other access modes the children are locked with. We can also see how intent locks both IS and IX mode are compatible with each other, with IS having a much loose privileges than IX due to the nature of the X mode. Now we can generalize this tree into a directed acyclic graph to cover non-hierarchical locks. A tree is a simple DAG, but in reality, the hierarchy might involve instances where a node have multiple ancestors on the same level. To implement the idea that one should lock all the parents of the node in the DAG, there are protocols that ensures that these are followed. To request an S or IS lock, at least one parent must be on IS mode. This ensures that there is a path to the root in IS mode, and none of the ancestors in this path can be granted to another transaction in IS incompatible mode. To request an X, SIX, or X lock, all parents must be on IX or greater mode. This ensures that all ancestors will be held on IX or greater mode, and no ancestors can be held by others in IX incompatible mode. All of our examples earlier are related to static lock graphs. However, a more realistic situation is when areas, files, and indices are dynamically created and destroyed, and of course, records are continuously inserted, updated, and deleted. So, we need to implement index interval locks, which basically filters the records based on a certain index value and locks those filtered results. In this manner, we can come up with partitions based on the key values available in the records. As a result, when an index field is updated, it and its parent record move from one index interval to another. As an example, suppose one student moves from UP Baguio to UP Diliman. His records will leave the UP Baguio index interval and will join the UP Diliman index interval. When the student was inserted in UP Diliman, it joins the interval containing the new field, and it also joins the file containing the interval. Therefore, we can follow the same protocol for non-hierarchical locks, but we will extend it to support this scenario. The lock protocol for changing the parents of a node is, before moving a node in the lock graph, the node must be implicitly or explicitly granted in X mode in both its old and its new position in the graph. Further, the node must not be moved in such a way as to create a cycle in the graph. Now, consistency is one of the properties of a database that guarantees reliable processing of transactions. Databases are said to be consistent if it satisfies the assertions or criteria about the data. However, they sometimes become temporarily inconsistent in order to transform it to a new consistent state. For example, adding a new student after registration would leave some fields inconsistent and will only be consistent until the process is completed. To address this, we will use the concept of transactions. Transactions are groups of sequences of atomic actions that transform one consistent state to another. They preserve consistency by undoing a failed transaction and enforcing the assertions, which means that transactions are also the units of recovery. Now, how does this relate to locking? For non-concurring transactions, each transaction will be able to see the consistent state the transaction before them left. But for concurrent transactions, These states are not really visible, so there are chances that the transaction will be using a previous consistent state, but apparently another concurrent transaction is using the same consistent state and will produce a totally different consistent state after. So locking ensures consistency in the inputs of each transaction. These lock protocols are also used by transaction to guarantee itself a certain degree of consistency independent of the behavior of other transactions. Now, before we dive down into the degrees of consistency, let us discuss some definitions first. A commit happens when a transaction removes its right to reverse its write actions, making the new value available to all other transactions. We say a transaction is dirty when the outputs of the actions are not yet committed. Now, some locks can be held on a short or long duration. When we say short duration, these locks are held for a duration of the single action. And if we say long duration, these locks are held until the end of transaction or all rights have been committed. Given a transaction T, we can define the degrees of consistency based on the implementation and how the lock protocol runs. A degree 0 consistent transaction T does not overwrite dirty data of other transactions. This prevents updating uncommitted updates of others, and it's considered unrecoverable since they commit outputs before the end of transactions. As to its lock protocol, the transaction sets a possibly short exclusive lock on any data it dirties. A degree 1 consistent transaction combines a new implementation process together with the degree 0 implementation. On top of not overwriting dirty data of other transactions, the transaction also does not commit any writes before the end of transaction. This guarantees that all transactions are recoverable, and this is the reason why databases require at least degree 1 consistency. In this sense, the transaction is well formed and with respect to writes, and it is two-faced with respect to writes as well. Its lock protocol sets a long exclusive lock on any data it writes or dirties. Now, a degree 2 consistency transaction combines the degree 1 properties with another one, which is does not read dirty data of other transactions. This isolates a transaction from the uncommitted data of other transactions. Because with degree 1 alone, a transaction might read uncommitted values which are subsequently updated or are undone. Its lock protocol combines with degree 1 protocol, and at the same time, it sets a possibly short share lock on any data it reads. Now, the degree 3 protocol performs as if the transaction is alone. Combining degree 2 implementation, other transactions do not read any data read by transaction T before the transaction is completed. It isolates the transaction from dirty relationships among entities. With degree 2 alone, transaction may read two different committed values if it reads the same entity twice. This is because a transaction which updates the entity could begin, update, and end in the interval of time between the two reads. Its lock protocol combines the degree 1 lock protocol, and it also sets a long share lock on any data it reads. The initial definition of consistency was based on dirty data, and that definition is too restrictive in the sense that the consistency will not require that the transaction hold all locks to the end of transaction. Rather, the constraint that the transaction be two-faced is adequate to ensure consistency. In this case, dirty data may happen due to scheduling. Hence, we can make the notion of dirty data explicit by considering the execution of a transaction in the context of other concurrently running transactions using a schedule of transactions. Since we have an audit trail of what is happening, dirty writes of a transaction are now made explicit. In case of serial transactions or one-at-a-time transactions, they have no induced consistency because no transaction sees dirty data. But the problem arises with regards to concurrent transactions. Concurrency constrains the schedule. For the reason that one transaction may lock a specific For the reason that one may request a lock on a resource while a concurrently transaction may request on that locked resource at the same time. And this defines the legality of a schedule. A schedule is legal if it does not schedule a lock action on an entity which has been locked by another transaction. In this case, a formal definition of a schedule is provided in the paper. A transaction T runs at degree 0, 1, 2, or 3 consistency in Schedule S if that transaction sees degree 0, 1, 2, or 3 consistency in S. And also, if all transactions run at degree 0, 1, 2, or 3 consistency in Schedule S, then S is said to be a degree 0 consistent schedule. Schedule can also define the dependency of transactions, which are transactions whose inputs are dependent on other transactions' output. If some transaction is both before and after transaction in some schedule, then no serial schedule could give such results, and this concurrency introduced inconsistency. On the other hand, if all relevant transactions are either before or after T, but not both, then transaction T will see a consistent state at a certain degree. This dependency definition is usually used as a proof technique for discussing schedules and recovery issues. To summarize, Gray presented a summary of the consistency degrees in terms of the different issues, either for committed data issues, the dirty data issues, lock protocols, and so on. And to close the paper itself, they also presented the presence of these locks and degrees of consistency in existing systems as of the writing. The first one is to introduce the IMS-VS, which implements a two-level lock hierarchy called the segment types and the segments. And at the basic level, it provides a degree 2 consistency, but you can obtain degree 3 by specifying the exclusive option. Another system is the DMS 1100, which also implements a two-level lock hierarchy, areas, and the pages within the areas. It also provides degree 2 consistency using exclusive and temporary locks. With that, I would like to thank you for listening and hope you got something from this presentation. Have a great day. Thank you.